This is Mrs. O'Neill for AP Chemistry, Chapter 16, Section 6, Part 2, these weak acid problems. So let's look at these problems. First of all, I should have given you this like as a half a sheet. If I didn't, hopefully one of you will remind me to make copies for you. This is kind of like those nice little flow charts that Mr. Bozeman gives you. However, this is just a way of getting from one place to another. Very similar to that stoichiometry flow chart that I showed you many moons ago. So if we start here using pH, we can end up here with Kb and kind of following the arrows. Yes, that looks like a nightmare, but that's what we're going to need to know how to do. We need to know how these are related to each other and how we can get from one place to another using pH, Kw, Kb, and of course those balanced chemical equations. Those were those general equations that Mr. Bozeman Science gave you as well. So let's look at example number 1. You have 0.1 molar of this HCHO2. I have no idea what that is, but I do know, and you should know, that it is weak because it is not on our list. This is really nice of them, though. They actually give us a nice reaction. If they didn't give us the reaction, I would say, well, I have one H, so I know it's an acid. I'm going to take it away. That's my H+, plus whatever is left over to the negative power. In this case, it's -1. They give us a pH, though. That's very interesting. They give us a pH. They want us to calculate K. They want us to calculate that equilibrium constant. Well, that would be products over reactants, but they're not really giving me any concentration numbers. But they're giving us a pH value. Look at that cheat sheet. Is there a way to get from pH to the H+ concentration, maybe? Hint, 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 right? And then we'll figure out this percent of acid that is being ionized. So again, as a reminder, this is the initial concentration of our weak acid molecule. We need to find the concentrations of all of these substances at equilibrium. So again, products over reactants, they were all AQ in solution, so they're all going to be part of the expression. But this is what we're solving for, but we don't have any numbers to put in. So like I said before, we're going to find that concentration of H+ from the pH value they gave us. Woohoo! This is now going to be the H+ concentration at equilibrium. From there, we're going to use that icebox again. Okay, so we learned that icebox in our regular general equilibrium reactions. We are now going to use it with our weak acids and weak bases. So calculate that H+ from the pH. If you remember how to do that, pause the video, find that answer, and then play to see the answers. Should have gotten that equals the 2.38. What are we going to do to that number? We're going to take that anti-log, right? 10 to the negative 2.38. Get our H+ concentration of 4.2 times 10 to the negative 3. Again, molarity. And this again is going to be at equilibrium. So icebox, woohoo! So what do we know so far? We know this. We know that this is our initial value of our weak acid. And of course, we have nothing to start with in our ions. Now, because of that H+ concentration that we found, that's at equilibrium. That is now going to be our change, right? So again, we add that change to our products, we subtract our change from our reactants, and notice we're dealing with all ones for coefficients, which is nice. We don't have to worry about multiplying or dividing our change numbers. Now we actually do the math like we did before, right? The 0.1 minus our change and the zeros plus our change to get all three substances concentration at equilibrium. Now we can go back and solve for our Ka. Bada bing, bada boom, do it in your calculator, and that should be your answer. Couple of things to notice. It is 2 sig figs. The constant has no units, and usually our Ka value is between 10 to the negative 3 and 10 to the negative 10. Now, how do we do that percent ionization? Well, again, just like before, percent always, always, always means part to a whole. Well, what part are we dealing with? Well, we're dealing with the amount that dissociated. In other words, that H+ concentration at equilibrium is going to be the part that dissociated. The whole part, or the whole amount would be the initial concentration of our weak acid they gave us. So again, our Part is our H plus concentration, and the whole is the initial concentration. And of course, it's a percent, so we're multiplying by 100. So plug and chug our numbers. Again, pause if you need to. Make sure you can do it in your calculator and get that answer. Again, it's a percent, so our unit is percent. So can you pause the video and figure out to do, it's basically the same thing. How nice. They give you a 0.02 solution of our weak acid. Again, if you did not know what this was, they did not have to tell you that it was the B vitamin. You would know to take that H away and what's left over into the negative sense. So again, they're giving you a pH value, calculate Ka, and percent ionization. Very similar to what we just did. So pause the video, see if you can come up with that ice box, plug and chug, and that percent ionization. So here's our pH equals the negative log of H plus. We're kind of plugging and chugging. We're taking that anti-log and we're getting a value at equilibrium. We're filling in that ice box next. So again, hopefully you tried to do this. This is that 5.5 times 10 to the negative 4 H plus concentration that we got from the pH. Now that becomes our change, and everything's a 1-to-1 ratio. So we're subtracting, we're adding. Now we can plug and chug into our Ka expression. Hopefully you got that as an answer. And again, no units because it's K, it's a constant. And the only thing that changes that constant is temperature. So did you figure out the percent ionization? If not, I would do it now. And again, we have a percent there because it is a percent unit, okay? Percent is a unit. All right, so example 3 is slightly different. Again, they're giving us iodic acid, which is a weak acid. I do not see a reaction here. So if I look at this, I'm going to say, all right, I'm going to take an H away, and what's left over is IO3 negative 1. Now they're giving us the Ka value at a certain temperature. Interesting that they're giving it to us at a temperature. Didn't I just say K can vary with temperature differences, right? Okay, so we want to go work our way backwards now, and we need that hydronium ion, or that H plus ion concentration. All right, here we go. That ice box again, right? So if we fill in that ice box, we know the initial concentration, we know that our products are starting at 0, but do we know anything else? Absolutely not. This is where that gosh darn X is going to come from. Now we can use, well, we've changed our X. At equilibrium is going to be our X, and that's going to be our change. So again, we're subtracting here 1 minus X, 0 plus X, and 0 plus X. Now we're going to go back and use that equation. Now I'm going to show you this all at one shot, but try to pay attention little by little. So again, here's our K expression. This is now we're going to plug and chug because they give us that Ka value, but now here's our X's. That's where our X squared comes from. And of course, our equilibrium concentration of our weak acid is 1 minus that X. Well, did you look over here? We're going to assume that that X is so small that we're going to actually just get rid of it. Because if we don't get rid of it, we're going to have to use that gosh darn quadratic equation, and yuck, yuck, yuck. So on the AP exam, I'm going to strongly suggest to you, they know this rule. You should point it out to them though. So if you have an expression like this that you have to do this algebraically, I would circle this, or I would make a little notation here that says, I'm going to assume X is less than 5%, so I'm going to get rid of it. Then it's a little bit easier to deal with, right? Then we're going to multiply. We're going to have our X squared, which means we have to take the square root from each side, and we get our concentration of 0.411. By the way, what am I missing here, right? I'm missing molarity here. I'm missing that unit. So make sure you have that in your notes. So now what you should do though, and you might have to do this in college, you will not have to do this as of now on the AP exam unless they feel like, well, these guys have all of these fancy dancy calculators that maybe you can do the quadratic within seconds. I don't know. But if we were to go back and plug and chug that amount that we got to see how much it ionized, it's actually way more than that 5%, which means we would have had to go back, solve for X, solve for that quadratic, and then you would have two values, right? You'd have a positive value and a negative value, and then use that positive value for those of you that are mathematicians. So give this some thought and see if you can come up with an answer. Again, it's just like I was talking about, right? That 5% rule. So polyprotic acids means that you can have more than one H that's donated. Okay, so let's look at this as an example. Our phosphoric acid, H3PO4. Our first reaction is this. We take one H away and we're left with H2PO4 given a Ka1 value. We have another reaction then. This guy is going to also donate an H plus to water, forming this reaction and those products with a different Ka value. I want to remind you, right, every reaction has its own K value, its own constant. And it's going to do this one more time with another K value. All right, so what's going on here? It looks like my Ka values are getting smaller. Why? Well, this guy, again, even though we're talking about a weak acid, this is going to be our strongest weak acid of all three. So again, here we have acid 1, acid 2, acid 3, right? They're all acids because they all can give up a H plus. So what does that mean? Well, it's easier to remove that first proton. It's easier to remove that H plus, meaning that there's going to be a heck of a lot more ions. Aha, there's going to be a heck of a lot more ions here because it's a bigger number, right? This is the biggest number. It's going to have a lot more ions. It's going to be the strongest of the weak. Okay, so the Ka, as it becomes smaller, that means we have more H pluses that are removed. In other words, we have less ions. So we have more ions here because it's the strongest of the three weakest acids, and here we'd have a lot more molecules. So number one, the reaction would lie more to the right, more products, and number three, the reaction would lie more to the left, having more molecules. Okay, so hopefully that makes sense. So here's the titration curve of a diprotic acid, very similar to those reaction mechanisms, right? The reaction mechanisms, we had a couple of different hills to get over. Well, the same thing, if it's a diprotic acid, we basically have two titration curves happening as we titrate our weak acid with our strong base, which means we have two midpoints, we have two equivalence points, we have two of everything because it's diprotic. If it was triprotic, we'd even have another one. Okay, so can we answer the following questions? Pause. And did you get that? Next question. Pause. And did you get that? Again, now we're dealing with a base and not an acid. Pause and see if you can come up with an answer. Hopefully you got that. If not, that might be one you might say to Mrs. O'Neill, hey, that number 3, that quiz in your video notes, can we actually do the work for that? And maybe we can. How about number 4? And I'm giving you a big hint right here. So pause the video and can you put them in order? Hopefully you got letter A as your answer. Number 5, again, same type of thing. And did you get that as an answer? All right, we'll see you in class.